Hi, welcome to Calculus Discoveries with Lauren and Zach.
Today we've discovered a new type of approximation called Riemann sum approximations.
No way.
Yes way. Let's say we want to approximate the area under this curve. We can use rectangles. And that's how it's done.
For today's episode, we will be going over Riemann sum approximations.
But Lauren, what kind of Riemann sums are we talking about?
Well, Zach, we will be going over left, midpoint, and right Riemann sums, otherwise known as LRAM, MRAM, and RRAM.
Before we begin, let's refresh ourselves on what exactly we are approximating.
Riemann sums fall under the second branch of calculus called integrals.
Integration is really just another way to say area under the curve.
So when you integrate, you are simply finding the area between the curve and the axis.
Now let's look at three specific approximations.
Let's say you're given the function f of x equals x squared.
And this is the area you're trying to approximate.
We can break up the curve with subintervals along the x-axis.
Now, let's take a step back to geometry. How do you find the area of a rectangle?
Well, isn't that just the base length times the height length?
Yes, exactly. That's really all LRAM, RRAM, and MRAM are. The only difference is how you measure the height.
So let me see. For LRAM, you would use the left side of the rectangle. And for RRAM, you would use the right side of the rectangle. But what would you use for MRAM?
Well, the middle.
I think we're ready for some problems.
First, let's start by approximating the area under the curve of x cubed from 0 to 10. We can break it up into 5 even subintervals of 2, from 0 to 2, 4 to 6, 6 to 8, and 8 to 10. Now if you notice, these subintervals are going to tell us the base of our rectangles. However, we need to decide on which way we want to measure the height. I think it's easiest to start with LRAM, which we'll be using f of x for 0, 2, 4, 6, and 8 as our heights. It's important to note that we're not using f of 10 in any of our heights because f of 10 is on the right of the rectangle, and we are only using the left side. Now we can take our subinterval of 2 and multiply by each of the left heights. We get the left heights by plugging in the values into the function f of x is equal to x cubed. Now we can plug in 2 times each of the left heights. 0, 2, 4, 6, and 8. We got these values by plugging in each of our left subintervals into the function x cubed. By adding all these numbers together and multiplying by 2, we arrive at 1600, which is our approximation, if you remember, of x cubed from 0 to 10 using a left Riemann sum. Next, we'll move on to a little harder problem.
Now we will do an approximation using RRAM. We're given a table with x values and their corresponding y values. So we can do an RRAM approximation by using the base lengths times the right side of the height. Now notice that the x values are not evenly spaced, so the bases change. So we have to calculate each rectangle separately. So the first rectangle will have a base of 2 and a height of 7, since we're using the right side of the rectangle. The second one will have a base of 1 and a height of 9. The third will have a base of 2 and a height of 4. The fourth will have a base of 3 and a height of 8. The fifth will have a base of 1 and a height of 12. And the final one will have a base of 3 and a height of 2. So now we will multiply all of these out. And once you add this all together, this will be the integral of this function from 1 to 13 using an RRAM approximation. And this approximation should come out to 73.